So for Lab 5, I used one of Christoph Himmel's videos to analyze his trick on the impossible trampoline. The lab asks, has Christoph Himmel, CH, discovered a way to violate conservation of energy? CH performs tricks on a standard trampoline. One of his tricks is him landing back on the platform he falls from. For him to be able to do this and land in the exact same spot would require him to conserve all the energy he expels in the process to launch himself all the way back to the platform. The main question is, can a trampoline conserve energy so well that it returns CH to almost exactly the same spot? To do this, there can't be any energy lost from the system, which seems impossible, but CH seems to be able to do it. So my main goal for this lab is to create a viable prediction of the spring constant of CH's trampoline using Newton's second law and the energy principle, and then explain the forces on CH that allow him to return to the platform. I had to make quite a few assumptions for this lab because I used a video from the internet, and I don't know a lot about CH. So assuming that CH is about 5'10", and the average 5'10" male in 2012, when this video was recorded, was about 190 pounds, I made calculations about CH with him weighing about 86 kilograms with a height of 1.78 meters. To calibrate the tracker video for distance points, it looks like he's jumping off of a metal shipping crate. So I looked up the dimensions for a standard shipping crate and found it to be approximately 2.6 meters high. And then using an equation formed to determine the surface area of a human, I found CH's surface area to be 2.06 meters squared. But he falls on his back, so I used half of that as 1.03 meters squared. We definitely know of three forces acting on CH as he interacts with the trampoline. Because CH is jumping on Earth's surface, we know there is definitely the force of gravity and air resistance, and then obviously he receives a force from the trampoline. So the fact that he made it back to the pole with these three means that somehow he was able to adjust his force to make him return to the same spot. So my initial thinking was that he had pushed himself off the platform, or he jumped, or he had some sort of extra force. But if you watch his other videos, in a lot of them, he simply just falls off the edge. I found an article on CH that made two really good points. One, that he doesn't return to exactly the same spot, which is the reason why I chose the video clip that I did. It's extremely evident in my tracker video that CH does not return to exactly the same spot, but a significantly lower point on the pole. And then the second point from the article was that a lot of times he'll end his trick landing in a flip, causing his center of mass to be lower than when he jumped, which makes sense and would definitely help him counter a lack of returning force. So now we definitely know that CH had to have put his own force into the fall. The trampoline is not perfect, and we know that CH should not reach the same point simply because there is air resistance acting on him. He's able to land in approximately the same spot because if you look a little closer at the video, he starts his jump with a backflip. He throws his left leg back and launches himself into a spin, making another force evident in his path towards the trampoline, causing his velocity, and thus his force, just before hitting the trampoline to be greater than him simply falling from rest. If CH used all the force he possibly could, we can use his vertical to calculate how much energy he put into the jump. The average guy has a 0.8 meter vertical. If we use the potential gravitational energy equation, we find that he expelled 674.24 joules of energy. But if you look closely at the video, CH doesn't exactly push his hardest. I made the axis to where the origin is where he starts his backflip. He throws his leg, which makes it hard to calculate, so I measured the distance he moved going in the positive y direction. Because of the camera angle, we're looking up at CH, so any recorded upward motion is how much he actually pushes himself away from the pole, and I used that as the H value to find a more realistic energy for this situation at 232.6128 joules. If we look at the force of the trampoline, including all of the interacting forces, we can identify initial and final positions to ultimately solve for the push force. To find the magnitude of CH's push-off force, the initial position is just before touching the trampoline from the fall, and the final position of interest is the moment when the object receives the full force of the trampoline. CH's actual jump includes a push force from a backflip, which we solved earlier to be approximately 232.6128 joules. If we were to solve for the spring constant using the forces given, rather than using the energy principle, we'd find that the push force is equal to 665.8435 joules, which was calculated in VPython. Such a high number made me reconsider just how hard CH did push off the pole from his backflip, and if the actual motion of the backflip added to his downward force. But this number, 665.8, is assuming CH returns to exactly the same spot. And in the tracker video, you can see he doesn't quite hit the same mark, which makes sense in our analysis of his jump where we solved for his jump force, and it was significantly less, 232.6128 joules. The actual value of CH's push force is likely to be much less than 665 joules. If the trampoline were perfect and the object falling did not experience any external forces other than gravity, the trampoline's returning force would be twice the received force in the opposite direction. If the trampoline conserved all of the energy, the magnitudes of the two forces should be equal to each other, and they are in this perfect case. I personally do not have a square trampoline because they're really expensive and I am not an aspiring Olympian. Athletes typically use rectangle trampolines like the one that CH is using because they're tighter and allow the jumper to be launched a higher distance than a round trampoline would typically allow. Rectangle trampoline spring constant would be higher than round trampolines because the rectangle ones are made specifically to give the jumper more force, and the higher the force, the higher the spring constant. An experiment done with a regular round trampoline found the spring constant to be 1750.5512 newtons per meter. When we solve for CH's trampoline's spring constant, we would expect it to be greater than 1750. Looking at the total change of energy of CH and the trampoline, we can solve for the spring constant of his trampoline using the energy principle. CH's spring constant was found to be 1791.22 newtons per meter, which is significantly higher than the circle spring constant by 41 newtons per meter, which makes sense because the rectangular trampolines are made for jumping with more force. The computational model was used to calculate CH's rectangular trampoline spring constant using our knowledge of forces and treating the trampoline as a spring itself. If you look at the visual part of VPython, you'll see the trampoline modeled as a literal spring and CH as the blue mass. The code portion was used to calculate and print the spring constant and the magnitude of the push force right here. So the data obtained from the tracker video could not be used to plan for future tricks or anything like that because of the numerous assumptions I had to make. In addition to that, the camera angle, though making the tricks look even more cool, is not useful for tracking the jumper's movement. The camera falls and moves, and CH often falls out of the camera's visibility, leaving a lot of points to be approximated in the white space. The measuring point, the shipping crate, was difficult to align with because there was a sort of fisheye effect, making the crate slightly curved, which would definitely cause the data to differ from its true value.